Recording on. Hi, I'm Rick. Jeff, you can hear me, right? What's that? Okay, so yeah, Jack can hear me. Guys, you all can hear me, right? Okay, we'll wait for others, guys, okay? Hi, Darren.
Hi, sir.
Okay, you can hear me, right?
Yep.
Okay, good. How you guys doing? So at home. Okay, Catherine is here. Catherine, you can hear us, right? Hi, Catherine. I hope she can hear us. Okay. Guys, you already had some few classes online, or is this the first time?
This is the first time.
Okay. Okay, fine. You guys okay, right? Yeah. Was it hard to find the link or everything okay?
Nah, it was easy.
Okay. You guys on your computers or using your mobiles, or how you guys have connected?
I am using a laptop.
Okay. Hello? Okay. Yeah, it is go to Moodle. So how you trying to connect? Using your phone? Okay, so then go to Moodle. Go to the course page, Electrical Principles. Okay, so there you have separated with the heading Zoom meetings. Go to that Zoom meetings, okay? Zoom recordings, I'll put these videos after the class. Yeah. That's correct, yeah. Click on that. Yeah, that's correct, yeah. Yeah, you're here now, no? No, I'm waiting for others. So it is already started, but we are waiting for others, okay? Okay, now you can hear me on Zoom, right? Okay, great. Guys, 10 name. We have 9 of you here. Luca, okay. Guys, we'll wait another 5 minutes, okay, for others to come. So we have 9 students online now.
Hi, sir.
Hi. Who is that?
Jordan.
Okay, that's great.
just had our fundamentals class, so we're jumping straight onto your one.
So is it at the same time?
No, so I think it's 9 till 10. He just went a little bit over. So there'll be quite a few students still in that class.
Okay. Yeah, thing is if you have both classes at the same time, guys, yeah, you can join tomorrow. No, I mean if you guys can all attend this one, so that's okay.
Yeah.
So then we'll discuss it, okay? So what we can do with that one.
Yeah, you might be better starting like 10 minutes late, just for everyone to transition from that last class to this one, maybe.
Oh, okay, yeah.
Yeah.
That should be possible, yeah.
Good.
Okay. So now we have 13 students. We'll wait for others also, like maybe 5 minutes. Maybe, guys, okay. Yeah. Wait. Guys, our plan today is discuss about these inductors, okay? So that is our plan. So yeah, I will wait a little bit. So yeah, so now we have 13 participants in the class. That should be all right. Guys, did you notice that assignment is uploaded? So now it is in as assignment, not as a class test, okay? Earlier we had class test, and now we are changing it to assignment. So you guys can attend that one as a homework. Did you guys notice that, guys?
Yep, I noticed it. I just downloaded and printed it today.
Okay, that's great. Yeah. Your first lab is all okay. Guys, what is the situation of multisim? How many of you have access to multisim?
I don't have access to it. Is there a way we can log into the Polytech computers from home? Is there like a Citrix thing that we can download and access the servers from home?
I'm not very sure about that one. You need to check with ITS for that one. But guys, what about this option? Like they have this evaluation version, right? For some time you can use it, isn't it? Yeah, so some of you have access, right? Yeah, so I can see some replies. Yeah. Grant, yes. Derin, no. Cameron, yes. Yeah, so yeah. Guys, but only thing, I think evaluation version are, I think, only available for 7 days or 14 days, I think. That is the problem. So one thing you can do, guys, like, so when you have the lab work, so then you can start that evaluation version and complete it. Another thing, guys, I think, so they are detecting based on your email address. So you can create a couple of installation under different email address. That will also work. And also you have online version, but that is limited with limited functions, I think. You can't have all equipment and so on. That is the problem. Okay, guys. Okay, now shall we start the class, guys? Good morning to all of you. So yeah, Carlos is also here. Hi, Carlos. Yeah. Okay, now we have 17. Jason also joined with the class. Yeah, that is good number, guys. Okay, so guys, okay, we'll start the class. I hope you all noticed the assignment, guys. Okay, now your class test is like uploaded as an assignment. You all can attend to that at home. So first few question, it is a DC circuit theory. and this Ohm's law, Kirchhoff's voltage law. So we discuss similar questions. And also capacitor one, guys, you can attend. So we discuss similar question in the class. So today we are doing inductors. After today's class, you can attend this inductor part as well. Okay, we will discuss some problems as well, similar to that assignment. Yeah, guys, I have uploaded a slide set. So that is under, if you go to Moodle page, so go to this inductor section, electromagnetism section, guys. So under that, you can find few videos. Yes, you can find few videos, and also under that, you can find one PowerPoint slide set called lecture slides, electromagnetism. Can you all see that, guys? Okay, guys, can you all see that lecture slide?
Yeah, we can now.
Okay, so yeah, so on the screen as well as, can you guys locate that also on the Moodle? Okay. Can you all see this, guys? Okay, that's great. Okay, today, guys, we are planning to go through this one, okay? This slide set, and it covers everything. In addition to this slide set, I have uploaded few other also. So these are additional reading materials. At home, you guys can leisurely read them, okay? But it is not must. If you go through this slide set, that is good enough, okay? But if you want to learn further, so these are there. And also video, guys, time to time, I will point to videos. So then you guys can watch them and so learn certain concepts. Guys, in order to look at, so then what we cover, so best place to look at, guys, go to your module outline. So there, so if you download this module outline, yeah. So hope you guys can see this one.
So are you able to like screen record how you're getting to there from Moodle?
Yeah, so I can do that. Yeah, so yeah, so I'm speaking about, okay, share content. Okay, now can you guys see my browser? Guys, can you see my
Oh yeah,
browser?
yeah, we can now.
Okay, okay, now guys, locate your course here, Electrical Principles 2020. Now here, guys, under this home, you can find this module outline, right? So it is here.
Okay.
Okay, so that document is, I'm referring to that. And also, so electromagnetism, so these are the material, okay? So these few videos, and also so you have this slide set. Today we are discussing this slide set, and also these are the extra reading materials.
Okay.
Okay.
Yeah, that's good.
Okay.
Sweet,
Now,
thank you.
shall I go back to that?
Can you show us where the assignment is?
Okay.
Because
So
I can't find it.
Yeah, that's good. Yeah, it is under this tab, assessment and resources. If you scroll down.
Okay.
See. Go to assignment. So then you will see the document also. See.
Oh, okay. Yeah, so it's in the
Yeah.
Dropbox thing itself. Sweet.
Okay. Yeah, I think one already submitted. Okay.
And you. Oh, okay.
Oh.
So with the assignment, like, I'm not sure if all of us have access to printers
That's correct.
and all that,
Like
so we
maybe,
can just take a picture of our refill or whatever with all the answers. You're right
yeah,
with
that's
that?
correct. You can
Sweet.
take a photo, so and just paste on Word document and upload. That is good
Okay.
enough.
Awesome.
Even
Oh,
I
yeah.
don't have access to a scanner during the this time, guys.
Okay. Awesome.
I had to do the same thing. Yeah.
Sweet.
Guys, you all good? So you all can locate the assignment, module outline, and slides. All good, guys?
Yes, sir.
Okay. Okay. So then,
So,
okay. So then, guys, I'll go to this module outline. So if you go there, guys, so here you guys can see the indicative content and also in details. So you can see some of these content, guys, I covered through activities. But if you guys go through this point, you can understand, guys, we have covered all of them, but maybe different modes like activities and maybe slide time to time, likewise. Okay. But because now we don't have access to these actual components and also multisim, most of the time we are sticking to our slides. Okay. So under this, 1.5, guys, so we are discussing these terms. So today, I think we can finish these topics today. Okay, this is what we're going to cover. Are you guys clear? Guys, when you're deciding content, don't look at all the slides uploaded. So this is where to look at, okay? So this is your module outline. So there you can find all the topics. So I maybe, yeah, so maybe with different modes, I'm covering this content. Okay, hope you guys are okay with this. So you guys can visit that link anytime and download your module outline. So then after that, yeah, I will open the slide set. Okay, so we'll start this electromagnetism topic. Guys, go through these few questions. So these are similar questions that you need should be able to answer at the end of this class. Okay. So in your exam, you have one question from this electromagnetism area. Okay. So Faraday's law, Lenz's law, and also self-induction, mutual induction. And also you should be able to decide how this magnetic field applies on conductors, how the forces work, things like that. Okay, and you should be able to do this sort of calculation. So voltage induced, so when there's some current flow through a coil, things like that. So, and also when there's a magnetic field. So at the end of class, we will do this question, guys. Okay, we'll come back to this question and we'll work out each of them. And also when there's a current flow through a coil, so what will be the energy stored? So inductor also acting as temporary energy storage device like capacitor. Okay. And also this is also a very popular question that you get in your paper. So in this type of inductive circuit, we can't change current at once. And also when we change current, like it creates some voltage spikes. Okay. So these can damage your component like transistors. Because of that, we need to have some protection. So this question is about that. Okay. Okay. Now, guys, electromagnetism, that is actually some area in physics. Okay, where they study interaction between these charged particles. So the forces between this charged particle, positive and negative. So because of that, we can speak about this the spectrum also, where we have microwave, ultraviolet, and so on. So these are all a result of this type of particle. And yeah, so we don't need to go into details. So, but this is where some area of physics. But we are speaking about discussing about whatever important to this electronic side or electrical side. So then, guys, before we start this learning this one, magnetic fields, so just go to Moodle page. There I have uploaded one video, very good resource, 10-minute video. It is the first one in that set of video. Can you guys locate video with the title Inductors? Can you guys locate it?
Is it the Inductors explained thing?
That's correct, yeah.
Sweet.
Yeah, just watch that video, guys, all of you. I will try to play it here also. If you go to this electromagnetism topic, guys, I'm speaking about this first one, okay?
Hey there guys, Paul here from the engineering mindset. Wire will act as a video. We're going to give you the most. So when the circuit goes.
Okay guys, okay, now I'm playing it, okay?
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at inductors to learn how they work, where we use them and why they're important. Remember, electricity is dangerous and can be fatal. You should be qualified and competent to carry out any electrical work. So what is an inductor? An inductor is a component in an electrical circuit which stores energy in its magnetic field. It can release this energy almost instantly, and we'll see how it does that later on in this video. Being able to store and quickly release energy is a very important feature, and that's why we're going to use these in all sorts of circuits. Now, in our previous video, we looked at how capacitors work. Do check that out if you haven't already, links down below. So how does an inductor work? I want you to first think about water flowing through some pipes. There is a pump which pushes this water, and the pump is equivalent to our battery in the circuit. The pipe will split into two branches, and the pipes are equivalent to our wires. One branch has a pipe with a reducer in it, and that reduction makes it a little harder for water to flow through it. So the reducer is equivalent to resistance in our electrical circuit. The other branch has a water wheel built into it. The water wheel can rotate, and the water flowing through it will cause it to rotate. The wheel is very heavy though, so it takes some time to get it up to speed, and the water has to keep pushing against this to get it to move. This water wheel is going to be equivalent to our inductor. When we first start the pump, the water is going to flow, and it wants to get back to the pump as this is a closed loop. This is just like when electrons leave the battery, they flow and try and get back to the other side of the battery. By the way, in these animations, I use electron flow, which is from negative to positive, but you might be used to seeing conventional flow, which is from positive to negative. Just be aware of the two and which one we're using. So as the water flows, it reaches the branches and has to now decide which path to take. The water pushes against the wheel, but the wheel is going to take some time to get moving, and so it's adding a lot of resistance to the pipe, making it too difficult for the water to flow through this path. Therefore, the water will instead take the path of the reducer because it can flow straight through this and get back to the pump much easier. As the water keeps pushing, the wheel will begin to turn faster and faster until it reaches its maximum speed. Now, the wheel doesn't provide almost any resistance, so the water can flow through this path much easier than the path with the reducer in it. The water will pretty much stop flowing through the reducer, and it will all now flow through the water wheel. When we turn off the pump, no more water will enter the system, but the water wheel is going so fast it can't just stop, it has inertia. As it keeps rotating, it will now push the water and act like a pump. The water will flow around the loop back on itself until the resistance in the pipes and the reducer slows the water down enough that the wheel stops spinning. We can therefore turn the pump on and off, and the water wheel will keep the water moving for a short duration during these interruptions. We get a very similar scenario when we connect an inductor in parallel with a resistive load such as a lamp. This is the same circuit as we just saw, but I've just wired it more neatly. When we power the circuit, the electrons are going to first flow through the lamp and power it. Very little current will flow through the inductor because of its resistance at first is too large. The resistance will reduce and allow more current to flow. Eventually, the inductor provides nearly no resistance, and so the electrons will prefer to take this path back to the power source rather than through the lamp, so the lamp will turn off. When we disconnect the power supply, the inductor is going to continue pushing electrons around in a loop and through the lamp until the resistance dissipates the energy. So what's happening in the inductor for it to act like this? Well, when we pass electrical current through a wire, the wire will generate a magnetic field around it. We can actually see this magnetic field by placing compasses around the wire. When we pass a current through the wire, the compasses will move and align with the magnetic field. When we reverse the direction of the current, the magnetic field reverses, and so the compasses will also reverse direction to align with this. The more current we pass through the wire, the larger the magnetic field becomes. When we wrap the wire into a coil, each wire again produces a magnetic field, but now it will all merge together and form one large, more powerful magnetic field. We can see the magnetic field of a magnet just by sprinkling some iron filings over the magnet, which will reveal the magnetic flux lines. When the electricity supply is off, no magnetic field exists. But when we connect the power supply, current will begin to flow through the coil, so a magnetic field will begin to form and increase in size up to its maximum. The magnetic field is storing energy. When the power is cut, the magnetic field will begin to collapse, and so the magnetic field will be converted into electrical energy, and this pushes the electrons along. In reality, it's going to happen incredibly fast. I've just slowed these animations down to make it easier to see and understand. So why does it do this? Well, inductors don't like changing current. They want everything to remain the same. When the current increases, they try to stop it with an opposing force. When the current decreases, they try to stop it by pushing electrons out to try and keep it the way it was. So when the circuit goes from off to on, there will be a change in current. It has increased. The inductor is going to try to stop this, and so it creates an opposing force, and there's a back EMF, or an electromotive force. This back EMF opposes the force which created it. In this case, that's the current flowing through the inductor from the battery. Some current is still going to flow through though. And as it does, it generates a magnetic field which will gradually increase. As it increases, more and more current will flow through the inductor, and the back EMF will eventually fade away. The magnetic field will reach its maximum and the current stabilizes. The inductor no longer resists the flow of current and acts like a normal piece of wire. This creates a very easy path for the electrons to flow back to the battery, much easier than flowing through the lamp. So the electrons will flow through the inductor and the lamp will no longer shine. When we cut the power, the inductor realizes that there has been a reduction in current. It doesn't like this and tries to keep it constant, so it's going to push electrons out and try to stabilize it. This will power the light up. Remember, the magnetic field has stored energy from the electrons flowing through it, and it will convert this back into electrical energy to try and stabilize the current flow. But the magnetic field will only exist when the current passes through the wire, and so as the current decreases from the resistance of the circuit, the magnetic field collapses until it no longer provides any power. If we connected a resistor and an inductor in separate circuits to an oscilloscope, then we can visually see the effects. When no current flows, the line is constant and flat at zero. But when we pass current through the resistor, we get an instant vertical plot straight up, and then the flat line continues at a certain value. But when we connect an inductor and pass current through it, it will not instantly rise up. It will gradually increase and form a curved profile, eventually continuing at a flat rate. When we stop the current flowing through the resistor, it again instantly drops and we get this sudden vertical line back down to zero. But when we stop the current through the inductor, the current continues and we get another curved profile down to zero. This shows us how the inductor resists the initial increase and also tries to prevent the decrease. By the way, we've covered electrical current in detail in a previous video. Do check that out, links down below. What do inductors look like? Inductors in circuit boards will look something like this. Basically just some copper wire wrapped around a cylinder or a ring. We do get some other designs which have some casing over. This casing is usually to shield the magnetic field and prevent this from interfering with other components. We will see inductors represented on engineering drawings with symbols like these. Something to remember is that everything with a coiled wire will act as an inductor. That includes motors, transformers, and relays. So what do we use inductors for? We use them in boost converters to increase the DC output voltage while decreasing the current. We can use them to choke an AC supply and only allow DC to pass. We can use them to filter and separate different frequencies. And obviously, we also use them for transformers, motors, and relays. How do we measure inductance? We measure the inductance of an inductor in the unit of Henry with a capital H. The larger the number, the higher the inductance. The higher the inductance, the more energy we can store and provide. It will also take longer for the magnetic field to build, and the back EMF will take longer to overcome. You can't measure inductance with a standard multimeter, although you can get some models with this function built in, but it won't give you the most accurate results. That might be okay for you, it depends what you're using it for. To measure inductance accurately, we need to use an Rlc meter. We simply connect the inductor to the unit and it will run a quick test to measure the values. Okay guys, that's it for this video, but to continue your learning, then check out one of the videos on screen.
Guys, you all watch that video?
Yeah.
Okay. So then we'll go back to our slide set. Yeah. Okay. Okay guys, I hope you got a good understanding about these inductors, but we'll go through this slide set as well. You guys can watch that video again at home guys, okay? So yeah, so now if you look at magnet guys, so we can see magnetic field around this magnet. So this magnetic field, if you guys can remember in that video, so it appears like this, right? So like these lines, and also we have like standard, so we say this magnetic lines appear across this something like this. So that means from north pole to south pole. Is that clear guys? That is how we mark them, okay? From north pole to south pole. Is that clear guys? Now generally guys, if you took two magnets, so what happened among this north pole and north pole if they put their closer? Do they attract each other or repel? North pole to north pole? Guys, what you think? Guys, what you think? North pole to north pole, what will happen? Will they attract each other or repel?
Repel.
North pole, yeah, that's correct. North pole to north pole. So when they put in close, so what happened is they repel, right? So reason what happened guys, so if you look at this magnetic flux lines, so when they are like this, okay, so when they are in same direction, so they repel each other, okay. Now if you look at this second example, what happened is we put north pole and south pole, then what happened is they attract each other. So you can see some magnetic flux lines appear like this, okay. So they attract each other. So then again, so this north pole to this south pole, you can see some magnetic flux lines. You can use iron powder to observe these flux lines, but you can't observe the direction. So that is standard. So we think, so these magnetic lines appear from north pole to south pole, okay. So when it is south and north, they attract each other. Now this is what happened when you put this north pole to north pole in close proximity. So then this is what happened. So then again, because these flux lines appear to same direction, they start to repel, okay. Is that clear guys? Guys, is that clear? Okay. Okay, great, guys. Okay. So, okay. Now that is one important thing. Most of the theories that we discuss based on this principle, okay? We discuss about what happened when we have magnetic field across wire, so and so. So this is important thing. Okay. Then guys, so we speak about this magnetic flux. So magnetic flux in real world, so we can observe by using iron powder. So, and also direction. So that is something that we imagine. So that is some standard. To represent this magnetic flux, we use phi, okay, Greek letter phi. So yeah. And also the unit that we use to measure this magnetic flux line, that is Weber. So here we use Weber to measure magnetic flux. Then guys, so we represent it this with this character phi, and also, so here it is not 108. If you open this slide set in your computer, guys, it is 10 to the power 8. Okay. So 1 Weber. So Weber means unit. What we mean by 1 Weber is 10 to the power 8 lines. Is that clear, guys?
Yes.
So when across magnet, when there are some magnetic lines, so when we have 10 to the power 8 line, that's a big figure. That many lines we have magnetic flux of 1 Weber. That is the idea. Okay. Okay. So then again, Weber also we can have milliweber, microweber, and so on based on our quantity. So we have to use yeah. So then we speak about magnetic flux density. If you look at some surface, so what is the strength of that magnetic field? To measure that one, so we can use this magnetic flux density. Okay, so this is term is we use Tesla to measure magnetic flux density, and this is the equation to calculate magnetic flux density in given surface. Is that clear, guys? So here we have phi, that is magnetic flux. So this is area. So then this gives you the density B. So the SI unit of a magnetic flux density, that is Weber per square meter. Okay, Weber per square meter. So then we use Tesla T to measure this one. SI unit is Weber per square meter. Is that clear, guys? Guys, is that clear? We have two quantities, that is magnetic flux and also magnetic flux density. Okay. Flux density means flux per given surface area. Okay. SI unit for magnetic flux density, that is Weber per square meter, and also we use Tesla. Tesla is not the SI unit. This is the SI unit, but we have one unit, that is Tesla. So then, guys, look at this question. See how we solve that one. Read the question and try to find flux density in each of these cases. Read the question carefully. So here the equation to use, it is flux density, that is equal. Okay. According to this question, so this 1 dot represent 100 line, or it is 1 microweber. Try that first part A, guys. Try to solve that one. Just all you need to do is apply this equation, okay? And also you need to calculate flux here. First tell me what is the magnetic flux in this surface? how many dots appear on this surface, guys?
7 by 7.
That's correct. Good. That is 49. Yeah, very good. Now it says like this one dot represent 100 lines. So altogether, how many lines? Very good. 49,000, right? This many lines. Okay. Now, if there are 10 to the power 8 lines, we call that is Weber. 1 Weber. Okay. Now, in this case, what is the quantity? So this 100 line mean 1 microweber, right? So then in microweber, how much? What is the flux here? Yes, guys. In microweber, how much is this?
49 microwebers.
Very good. Yeah, it is 49 microweber. Okay, because this one line mean so 1 microweber. So it is, yeah, guys. It is 49 microweber. Okay, because this one dot mean it's clearly say that 1 microweber. So altogether we have 49 dots. That mean flux is 49 microweber. Or maybe you can get this figure by dividing this many lines by 10 to the power 8 also. Okay, that also gives you figure in microweber. Or so this gives you Weber. You can later convert it into microweber. So then you are getting this value. Are you guys all agree with this? So the flux is 49 microweber. Now how we calculate the flux density? Just apply this equation, guys. What is the surface area? Now you need to find the surface area. Yeah, very good. Yeah, that's correct. So that's correct.
6.
So the surface area, you need to calculate this in meters, right? So that is 2.5 multiplied by 2.5, 10 to the power negative. What is the figure, guys? 100 centimeter is equal to 1 meter. Okay, so that means if you want to convert, yeah, so centimeter into meter, you have to multiply by 10 to the power negative 2. But here we are speaking about area. Then how we convert square centimeter into square meter? 10 to the power?
Negative 2.
Is it 2 or 4? Because we need to convert this one to centimeter and also this one. 10 to the power negative 2 multiplied by 10 to the power negative 2.
10 to the power minus 4.
Yeah, that's correct. Yeah, it's minus 4. Okay. Now, how we calculate the answer? The flux density 49 multiplied by 10 to the power negative 6 because it is microweber multiplied by 2.5 divided by 2.5 10 to the power negative 4. Now, what will be the answer, guys?
Zero 0.0784.
0.0.
784.
That's correct. Yeah. So when you convert, yeah, very good, very good. So when you convert it into Tesla, so we can write it like 78.4 or maybe 7.84 10 to the power negative 2, right? 7.84 10 to the power negative 2 Tesla. You guys agree with this answer? Okay, guys, you all agree? Guys, you got the same answer? Guys, you all agree? Yes. Okay, so most of you got the same answer. Okay, guys. Okay, then guys, same way, attend the second part, part B. Try to calculate flux density in second surface. Okay, the equation is B is equal flux divided by area. Okay, guys, now what is the flux here?
72.
Okay, very good. 72. How we calculate here? 1, 2, 3, 4, 5, 6. It is 6. 1, 2, 3, 4 is 6, 7, 8, 9, 10, 11, 12. Okay, 6 multiplied by 12. Okay, so that is how we get 72. So what is the unit here?
Weber.
Yeah, microweber, no? Microweber. Microweber. So now, guys, what is the area here? A is equal 2.5 multiplied by 5, 10 to the power negative 4. You guys agree? Okay, now you know flux and also you know the area. Now find what is the flux density here. Yes, guys, what's the answer?
57600.
Okay, so this is what you get, right? 0.0576. You guys got this answer? Unit is Tesla, right? Very good. Yeah, that's correct. So now we can write it properly. 5.76 Tesla, right? Sorry, 10 to the power negative 2 Tesla. Yeah. You guys agree?
Yeah.
Yeah. Answer is, guys, 5.76 10 to the power negative 2 Tesla. Okay, now that is the answer. I hope you all got that answer, guys. Okay, that is very easy question. Okay, we'll move to next slide. Okay, here, guys, if you want to double check your answer, or maybe if you want to work out again, so here you have the procedure, right? So now, guys, so when we magnetize a material, so what actually happens? So this is what happens. So we have magnetic domains in a material. It can be an iron. So then, so when we magnetize it, so we arrange them into same orientation. Okay. So like this, even all these particles point to one direction. No. That is also some virtual concept. Okay. So this direction, but maybe, so it has same orientation anyway. So when we have the same orientation, so it attracts some metal pieces, so it acts as a magnet. Now tell me, guys, so actual world, so what are the occasions that we use these magnets? Maybe permanent magnets, so, and also maybe temporary magnets. By using electromagnetic electricity also we can produce magnets. So some occasions, guys, so here also you can see some applications where we use them. Yes, guys. Yes. So we use in motors. That's correct. If you have remove the cover of this motor, you can see, guys, so we can see some permanent magnet, and also around that we can see some magnetic core, the coil core, and there are some different versions as well. Okay, very good. That is one occasion. And
Do we
also,
use it
have
in
you
speakers?
very good, yeah, speakers. And also, have you guys used this relay? Relays in
Yeah, you
circuits?
use it in
Yeah.
relays as well. Yeah.
Yeah, that's correct. So yeah, they are like transparent, right? Some relays transparent. We can see how they work also, right? And inside that, what happens is we have electromagnet. So when we power that relay, it attract one metal piece and connect with other, right? In that way, it acts as a switch. When there's no power to that one, it connect with another terminator, right? So likewise, it acts as two-way switch. And also, what happened in the speaker, guys? Have you guys removed cover of speaker?
Yeah.
Yeah, that's correct. Like, so there's a coil, right? Attached to this core of this cone of the speaker. And also when we apply some current to that one, relative to that current flow, so it go up and down, right? So when it go up and down, it creates some sound. So that is relative to that electric field or the electric current. So then in that way, it produces sound. Okay, that is what happened there in speaker. Okay. And also some cranes, they are using so to attract this metal pieces, so electromagnets. Okay, so there are many occasions where we use these magnetic materials. And also, guys, how about these transformers? Transformers also, we have some magnetic action. Okay, so with transformers we can produce electrical isolation, so and we can bring down the voltage, so reduce the voltage. So maybe like just think about 230 AC, we can convert it into step down into like 12 volt AC likewise. So the transformer also, so very good occasion. Yeah, that's good. Okay, guys. Okay, guys, now this is important curve, guys. So we call hysteresis curve, or if you look at this one, guys, so this curve is associated with materials. So metal, ferrite, likewise materials. Okay. So when you apply some magnetic force into material, we can convert it into magnet, right? For example, think about like so transformer core, when we apply some current, it convert it into magnet. Okay, now here what you see is, okay, what happened when we apply this magnetic field into a material? So when we increase the magnetic field intensity also increase like this. Okay, and it becomes saturated. Saturated mean, guys, it doesn't matter how much we push or we apply magnetic field, we can't convert it, we can't increase the magnetic flux density. Okay, we come to limit. Even in transformer core, you have this limit. That is very important. After this point, so if we continue the current to a transformer, it short circuit it and so create a big arc, or maybe it burn. Okay, because of that, because of any reason, we should not come to this point. We are saturating our transformer, or in this case, we are saturating our material. It can't further produce any magnetic field. Is that clear, guys? Guys, is that clear? Okay, now, then in this way, we can magnetize the material. So then again, we can reverse this magnetic force, or maybe first we can remove this magnetic force. Then what happened? It come back to this low intensity field, or maybe we can reduce the magnetic field density like this. But important thing, guys, so usually, for example, think about like we are applying some current to a conductor. So then it produces some voltage, or maybe when you apply voltage to a conductor, it produces some current, but that is proportional. So when we reduce the voltage, it comes back to same path. But here in this occasion, it is not following the same path. It follows different path. See, that is what we look at here, guys. Okay. And also to bring that magnetic field into zero, flux density to zero, we have to apply reverse force even. See, like this, reverse force. And when we further reduce that one, when we apply reverse force, so it creates some reverse magnetic field. Then when we reduce that one, again, it comes back to this position, so zero position. But for that, we need to apply, again, opposite force, okay? So then it go back to this position. And again, when we increase it, so it goes to like this. Now here, guys, look at this curve, right? So when we apply some magnetic field, so it magnetizes, but so it is coming back to zero in different path. And also not only that, we need to apply some reverse force also. See, reverse force, negative edge. Then, so here at this point, again, to bring it to zero, we need to apply some positive magnetic force. Then at this point, when we further increase it, it increases in this path. Okay. Okay. Now you guys got this curve, hysteresis curve. Guys, this is very important. Okay. Now think about transformer. Transformer, what is the type of current that we apply? So we apply something like this, right? Isn't it?
Yeah.
Okay. That means, guys, at this point, we create some magnetic field. So at this point, we create some opposite magnetic field. Okay. Is that clear, guys?
Yeah.
So when we create magnetic field like this, guys, it creates some magnetic field here. It produces some current through this conductor. Okay. Likewise. Now, tell me, guys, what you think about the width of this curve. In transformer, is it good to have thicker or so maybe what you think about this width? It is good to increase it or narrow it in transformer? Yeah, Sean has answered. Yeah. Yeah, good. What you guys think? When you select material for transformer, we have to go for material like this or material like this. In transformer, guys, so we should be able to replenish that magnetic field quickly. Quicker it is best. So then for transformers like occasion, we are using material like this, thin curve. But guys, when you want to produce some permanent magnetic field, you have to go for material like this. So that means when we magnetize it, it sustains that magnetic field for long time. So then this is the material to use. For transformer, we should be able to quickly change it, okay, to produce magnetic field in secondary winding. So because of that reason, we are using some material like this. So is that clear, guys? Guys, are you all okay? You got the concept here? Okay, so when we discuss further about this, so you will understand further, guys. For the moment, have this rough idea. So this is how you use magnetic material for different contexts, okay? Okay, good. We'll move to next slide. So now, guys, this is two rules. So I hope you guys have heard about this right-hand grip rule. Have you guys heard about that at your high school? Right-hand grip rule, guys? Okay. So, and also Fleming's left-hand rule and right-hand rule. Have you guys heard? now guys, this is different definition for same thing, right? So like this one, it is right-hand grip rule, and we can say corkscrew rule. Okay, so it is same thing. So it describes magnetic field when we have current flow through conductor. And this one, so this is one definition, okay? So we call FBI rule. So it is, guys, Fleming's rule and different version. So when we hold, the way we hold gun, so like we can represent it. Yeah, that's correct. Yeah. So if you guys, yeah. You guys, can you see? So it is something like this, guys. So we can hold, yeah, right hand rule. So something like this, okay? This is how we hold our hand. So then it is something similar to gun, right? So based on that, we call it is FBI rule, okay?
Yeah.
Okay, that is some funny idea, but so we have some formal definition of this one. So something like this. So FBI rule. We'll see how we apply this thing in circuits. Okay, now guys, look at this one. So we should be able to apply right-hand grip rule to context like this, okay? When we apply it here, guys. Okay. Guys. Now guys, so if I apply right-hand grip rule like this, okay? Your thumb should point the current direction. Then the rest of the finger represent the magnetic field. Is that clear, guys? In that way, so we can define direction of this magnetic field in this conductor, okay? But actually here in this case, it should be this way, isn't it, guys? Right-hand grip rule, okay? You guys agree? So when you apply right-hand grip rule, guys, so your thumb should point the direction of the current. So then you can see the direction of magnetic field that is perpendicular. That's correct. Is that clear, guys, to all of you? And also, so there's a way, guys, we represent this in a plain paper or something. So in a conductor, when we represent conductor like this, guys, so that means current come out, okay? And also when you represent a conductor like this means, guys, current go in, okay? Now each of these occasion, how you draw the magnetic field. So if you draw your conductor like this, what is the direction of magnetic field? So on a piece of paper, guys, so draw it. So this is perpendicular plane, right? So this is the cross section of the conductor. So now what will be the direction of magnetic field here? Just draw it on a paper, guys, to understand this concept. Right-hand grip rule. And also try this one, okay? So try to draw this one as well. Yeah, that's correct. That's correct. Some of you gave the answer. So now in this occasion, this is how magnetic field appear, guys. Use this right-hand grip rule to decide that one. You guys agree with that?
Yeah.
Okay. So what happened here? Second case. Sorry, guys. It is opposite. Sorry. So here in this occasion, current come out. Okay. Current come out. Okay. So then, so this is the way. So your finger should point outside, okay? So that means, so in this way, you can represent it, okay? So then what happened here? So second case, current go into the paper. So what happened there?
It'll just be the opposite.
Yeah, that's correct. Okay, so it will be this direction. You guys, is it clear, guys? Right hand grip rule. Guys, you all okay? Guys, this is important, right? You need to understand this. And also, guys, I have seen a few questions in your past papers from this rule, okay?
Hey, sir, in that case, is that picture not wrong?
Picture is wrong, actually. Yeah.
Okay.
I took this one from a book, okay? So
Yeah.
actually it is wrong. So it should be like
It
this,
should
okay?
be the counterclockwise, eh?
Yeah, that's
Yeah.
correct, yeah.
Okay, awesome.
So I took this picture from actually core textbooks of this module, but it need to be correct like this, okay? Okay, guys. Okay, now guys, yeah, let's move to next slide. See, this is how we apply it, guys, see? Okay. So when we have current flow like this, so in this way, we can apply it, guys. So we can represent that magnetic field like this. Now, guys, what happened when we have a coil? So when you have a coil, so just think about this conductor. So it carry current to this direction. Okay. If I draw the cross section of this coil, yeah. If I draw the, yeah, so look at this cross section. So what is the direction of current? Is it, guys, outside or inside at this point? Current going in or out, guys, here?
In.
So what you guys think? So this is the direction of the current, okay? So now if you look at this cross section, this side, so what will happen? Current coming out or going in? That means out of the paper, right? That means, guys, I can represent it like this, isn't it? Isn't that correct?
Yeah.
Like this, okay? Now, if you take a cross section from this side, what happened? Going into the paper, right? Because this is the direction.
Yeah.
Like this, okay? Now, each of these point, apply right hand grip rule, guys. So when you apply right hand grip rule, so you can see direction of this field, it is this direction, right?
Yeah.
Very good. So it is like this, right? Here also it is like this. Sorry, it's opposite. It should be like this, okay? Like this, and it create total field like this, okay? Now, because of that, guys, we know our formal definition. So these magnetic lines appear from north to south. So then this become a magnet. So where this is north, this is south. Is that clear, guys? By using right hand grip rule, you can easily decide direction of this magnetic field. Clear, guys? Guys, you all okay with this?
Yeah.
Guys, this can be one question, right, in your paper. So sometime you will get a coil like this, and you should be able to decide direction of the magnetic field. Okay. Okay, guys, if you look at this one also, so when we apply this rule like this, so then direction of the current, so then you should get north and south poles correctly. Okay. Now, guys, by using this rule, you should be able to decide the direction of the force and Yeah, direction of the current likewise. So here you have two rules, two Fleming's rule, left hand rule and right hand rule. So we can say FBI rule if you want. So tell me guys, can you guys remember when we apply each of these rule, right hand rule and left hand rule? Two occasions, generators and motors. Okay, which rule we apply to generator? Whether it is right or left rule. Yes guys, generators. Guys, how many of you are right-handers? Okay, how many of you guys? Majority, you should be right-handers, isn't it? Guys? Right, but yeah, so it's based on this answer anyway. Like how many of you right-handers? Majority should be right-handers, right? Only few should be left-handers. Are there any left-handers here? I think that is easy question. Okay, we have one, Felix. Okay. Okay, that means only few guys. So think in this way. Okay, in order to consume current, we have to produce it, right? So the producing current comes first. Okay, so then how we produce current? By using generator, right? So then our priority is our right hand, isn't it? So in that way, guys, we apply right hand rule to generators. So when we produce current, then we can consume with motors. So then left hand rule applies to motors. So that is a easy way to memorize those two rules. Okay, FBI rule or Fleming's right hand and left hand rules. Okay. 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 In here, guys. Yeah. So force represent by thumb. Okay. Force represent by thumb. Direction of current represent by middle finger, and direction of magnetic field represent by index finger. So that's okay. Even without this Fleming's left hand rule and right hand rule, so you can decide direction of the force by using right hand grip rule. Okay. Now look at this situation. If you look at this conductor, guys. So current coming out of the paper, isn't it? So then what will be the direction of magnetic field? With our rest of the fingers, we can find it, right? So this is the direction of magnetic field. So then magnetic lines will appear like this. Okay, now if you look at this red color line, okay, these appear to same direction, isn't it, guys? But if you look at this area, so these are opposite direction. See, these are opposite direction. That means these magnetic line should attract, while this magnetic field repel. That means, guys, we can easily find this current conductor should move to this direction, isn't it? So that is what happened here, guys. Because these lines attract, these lines attract, these lines repel because they are in same direction. So then because of that, final force appear to this direction. Is that clear, guys? Try to understand that. Apply right hand grip rule on this occasion and try to understand it. When magnetic lines appear to same direction, they repel, right? When magnetic line appears to opposite direction, they attract. So based on that, you should be able to decide direction of the force. Give me a minute, guys. One student trying to connect. Hello, Luis. Good. How about you? Oh, yeah, that's okay. Yeah, thing is like go to Moodle page. So there you can find separate tab like section called Zoom meeting. Then you can find that Zoom meeting link. Okay, just click on that one. So then you can join with the meeting. Okay, if you have any, yeah, electrical principles Moodle page. So then go to that Zoom meeting section. $10 Okay. Yeah. So can you? Yeah. So you can find Zoom meeting link for 10 o'clock. You have to go to this Zoom meeting tab. Okay. Did you see that tab? At the end, you should be able to find that one. Okay. So then click on that 10 o'clock meeting link. So then open it in Zoom. Got the connection? Okay, so then I'll tell you the meeting code if you want. That is 370 899 0899 899. Okay, 899 014 014. Third digit, third number 014. Yeah, yeah, 370 899 014 014. Got it? Okay. That's correct. Yeah. Okay. Okay. Bye. Sorry, guys. Did you try to understand this? Is that okay, guys? Guys, you guys all okay with this? You want me to explain it again? Okay, good. Guys, tell me whether you are okay with this. Can you guys decide the direction of that force based on this magnetic field? Guys, you all okay? Guys, tell me whether you're okay, because this is important, guys, because this is also some days where you get questions. Okay, because of that you
Can you
need
just
to
repeat it
understand
once
it.
more
Okay.
then, please?
Okay. Yeah. So now, in this occasion, what happened is, okay. So we have a magnetic field like this. Okay. Something like this, and we have conductor. So it carrying current to outside, okay, outside of the paper. Now, how we draw the magnetic field? So if you use a right-hand grip rule, guys, you can see it appear like this, okay, something like this. So then what will happen, guys? So how you decide the forces? If you look at this area, see, both are same direction, okay. So in magnetic field, when they are in both same direction, what will happen? So they repel, right? If you look at this area, so they are opposite direction, right? So that means they try to attract. So from this side, they pull like this. This side, they push like this. Then conductor, what is the overall force applied on this conductor? So it is like this. Got it, guys? So that means, so this conductor should move to this direction. Okay. We can decide that one by using right-hand grip rule. Is that clear, guys? Okay, are you good? Guys, you all got it? Guys, I hope this is clear to you now, okay? Okay, great. Okay. Okay, now guys, we come to this Faraday's law. Okay, according to Faraday's law, so this Faraday law is about, guys, a magnetic field in this coil like this, and also, yeah. So what is the voltage induced in this type of a coil? So what are the parameters depend on this? Okay. Okay, now read this one, guys. The amount of voltage induced in a coil is directly proportional to the rate of change of the magnetic field with respect to the coil. That means, guys, if you look at coil, so we can find coil in inductor and also these transformers, okay? So the voltage induced in the inductor directly proportional to the rate. So d phi over dt, this represents the rate, guys. If you want to calculate this one, so you need to do this one. Change in the magnetic field divided by time taken. So this should gives you the rate of magnetic field change. You guys agree with that? Okay. So the second parameter, it should be the number of turns. So now we are speaking about voltage induced in the inductor. Okay. Like this. So it depends on number of winding also. That means when we have a coil with many number of turns, it induces more voltage. Okay. In one sentence, guys, you can write Faraday's law like this. The voltage induced across a coil equals to the number of turns in the coil times rate of change of the magnetic flux. This is very important, guys. Okay, you need to memorize this one even. So voltage induced in a coil proportional to number of turns in that coil and also change in magnetic field. Okay. Okay, so now, guys, can you think of some practical applications of this one? Practical application. Now, guys, think about generator. Okay. Now, generator, what happens is we have a coil, we have magnet. Okay. So permanent magnet. Now, when we rotating this generator very fast, what you can expect? The voltage it produce. Is it go high or go down? When we rotate it fast, what will happen, guys? Yes, guys, tell me. Yeah, very good. It should go up, right? Because there, what happen is when we rotate that generator very fast, it increase rate of change in the magnetic flux, right? That means when this one go up, so voltage induced also should go up, right? You guys agree? Guys, you all agree? Okay, now, very good. Now think about a transformer, okay? Like this. Now, we have some n number of winding here, let's say n1, n2 in the secondary. Now, tell me guys, I'm increasing number of winding in the secondary side of the transformer. When n2 go high, what will happen to the V2? Voltage across secondary winding. I'm increasing the number of winding. So what should happen to the V2? So when we increase n, what will happen, guys? Guys, tell me what happened. So when I increase n, so what will happen to the V induced? Don't worry about that equation. So that is for transformer. Just tell me guys, when I increase n, just only look at the secondary side. Okay, I'm just increasing number of windings. So what will happen to the V induced? Very good, yeah. Guys, V induced should increase, right? When we increase number of turns, V induced should increase, right? It is very obvious. If you look at this equation, you can easily decide that, right? Okay, so now these are the important information that we can get from, derive from this rule, okay, or theorem. So you need to memorize this one. The voltage induced across a coil equals to number of turns in the coil times the rate of change. So equations, guys, you generally no need to memorize, okay? But this one says when you multiply change of the magnetic field with the number of turns, we should get the voltage induced, right? Okay, now attend this question, guys. Try to solve this problem. Okay, very good. That's correct. Guys, you all try that question. Correct. That's correct. Yeah, that's correct, Jason. Yeah. Guys, you all solved that one? Okay, how we solve that one? So our equation, that is V induced, that is equal N multiplied by dt. Okay, now in this question, N is given, that is 500 turns multiplied by d phi over dt, that means change of that magnetic field, that is also given, that is 8000 so microweber per second. So because it is 8000 microweber, we need to multiply it with 10 to the power negative 6. So then Weber per second. So yeah, so then this should give you guys the answer. So guys, tell me what's the answer. Some of you already got the correct answer. Guys, you all tried this question. Tell me the answer. Yeah, so most of you got the correct answer. That's correct, Tushan. So that is 4 volt. Okay. Guys, you all can see this properly, right? Whiteboard also. You have to be a bit of patience, so it is not good as our whiteboard in the classroom, but we have to manage with the available resource, guys. Guys, are you all okay? Guys, you all got the answer? Okay. Okay. This is the answer, guys. Here also you can find the answer. Okay, now second thing, guys. So Lenz's law. So Lenz's law speak about direction of this voltage. Now Faraday's law, it is about the magnitude of that voltage. Now Lenz's law, it is about the direction. When the current through coil changes, an induced voltage is created as a result of the changing electromagnetic field, and the polarity of that induced voltage is such that it always opposes the change in current. That means, guys, so according to Faraday's law, so V int, so that is equal N d phi over dt. Okay, now this is change. How we decide this d phi, guys? Like it is phi 2 minus phi 1. So then we can divide by dt. This is speak about delta phi change. Okay. Now this voltage is opposite to this change. That means, guys, we need to have negative sign like this. V induced should be opposed to the change. Okay. Now that is the meaning of Lenz's law. It should oppose the change. So we need to have this negative sign. That is about Lenz's law. Is that clear, guys? Guys, in that previous the first slide, we saw some question. So this is related to this one. Okay, in this way we can explain it. According to Lenz's law, like voltage induced, it should be the direction should be opposite to the change. So then we need to have this negative sign. Okay, Faraday's law speak about the magnitude. Okay, magnitude. So then Lenz's law speak about the direction. Is that clear, guys? Guys, is that clear? Guys, you all are with me? Okay. Guys, is it clear to all of you? Okay, that's good. Okay, good guys. To most of you, that is correct. Very good. Now, guys, please attend this question in this slide. So here, guys, you have a question. Please attend that. So for that one, guys, you need to use this equation, right? Force is equal BIL, okay? So force applies on conductor due to magnetic field, that is equal BIL. So B, that is magnetic flux density, I is the current, okay? And also L is the length exposed to that magnetic field, okay? Now here what happened is we have conductor through this magnetic field. So B is this magnetic field strength, okay? Current is current through this conductor. Length, maybe length of this magnet. So it decides the length which exposed to the magnetic field. So with that one, we can find the force in Newton. Just try this question. Yeah, that's good. Ahi, that is correct. Yeah. Just look at decimal, guys. Ahi. So the answer. Ahi, your answer is correct. Yeah. Guys, one important thing. Yeah. Yeah, Ahi, what's it? Guys, one important thing, I am marking your attendance based on this online attendance, okay? So those who attend the Zoom class, so you are getting presents for your attendance. So because of that important, guys, you need to attend the classes, okay? That's correct, yeah. That's correct. Dario, that's correct, yeah. That's correct. No classes tomorrow for you. Yeah. Guys, because most of you attend this class, there's no class for you being students. There's no class tomorrow, okay? But Jason, you guys have class, right? Okay, guys, let's work on this question. Okay. So now force is equal BIL. So now in this question, so what are the given values? So we'll write a simple L here. That's correct, yeah. So magnetic flux density, that is given 0.35 Tesla multiplied by current, that is 2 Ampere. And guys, tell me what is L here? What is L here, guys? So it is given that magnetic pole phase, that is 3 centimeter, right? So we have to use that one. That is the length of that conductor exposed to the magnetic field. So that should be 0.03. Very good, yeah. Now what will be the answer if you simplify this one? Yeah, very good. 0.021. So what is the unit, guys? Because we are speaking about force, very good. Yeah, it should be Newton. Very good. Yeah, that's good. Okay, very good, guys. You can do it yourself at home. So then we'll move to next slide. Okay, now this is also important concept, guys. Inductance. So we can define inductance like this, guys. It is inductance is a measure of coil ability to establish an induced voltage as result of change in its current, and that induced voltage is a direction to oppose the change in the current. But here, guys, so this means, so when we have inductor like this, so ability of this coil to create voltage when there's a current through that one, so we call inductance. We represent that with L. Okay, so now, so we can rewrite that earlier equation like this. Earlier equation we had N and change of the magnetic field, but here in this equation we have inductance. So this new term L, and also Diode. Diode mean, guys, change in the current flow. So that means, so actually in transformer, it is easier to explain what happened there when we go with this equation. So what we are changing is the current flow. When there's a change in the current flow, it creates change in the magnetic field and it creates voltage through that one. So that voltage is equal to L, or other way, it is a inductance multiplied by that change. Okay, this is very important. So that is how we define the inductance. And also, guys, like capacitor, inductor also appears energy storage device, but very temporary one. So that energy can be calculated with this equation, half Li square. Capacitor, that energy, that is half CV square, right? So we speak about capacity and also voltage, but in inductor we speak about current and inductance. That is E is equal half Li square. This is how we calculate it. Okay, half Li square. Is that clear, guys? Guys, is that clear? Now, guys, just think you want to create inductor yourself. You have roll of coil and also maybe ferrite core. So now, so in order to decide the inductance of that inductor, you have to follow this rule. L is equal n square, that means number of winding in that inductor, the permeability, so that is mu, so that is property of that magnetic core, and also area divided by L. Okay, with this one you can decide so how much is the inductance of given inductor. Okay, for that purpose we have this equation here. So is that clear, guys? Guys, is that clear? Okay, guys, if that is clear, guys, are you all okay with these three equations? Guys, you have any question? Guys, are you all okay? Okay. Guys, are you all okay? So are you all okay with this equation here? So relation between V induced and change in current, and also inductance, and also energy storage. It is similar to energy storage in capacitor. So are you guys okay? Okay. Are you guys okay with this equation over here? Okay, guys. Now, if that is okay, try to attend this question, guys. Then you will understand. Yeah. So you need to apply your third equation to solve this one. Okay. So answer is also there, but try to do it yourself, guys. You need to apply this equation over here, right? L is equal, inductance is equal, number of winding square multiplied by permeability multiplied by area divided by length. Now here, this surface is circular, okay? So because of that, to calculate the area, you have to apply pi r square. Try that, guys. Just see whether you are getting the same answer over here. Guys, you guys all got this answer? Okay. Okay, great. Guys, one small thing, guys, you want any break or shall we finish it by like, so like 12:30, guys? So what you guys prefer? You guys want a break or shall we finish it by like 12:30? So because it is okay. Tell me your choice, guys. Like we can finish it by 12:30 also, or maybe we can go to break if you want. Okay. Okay, most of you like 12:30, right? So yeah, so then it will be 2.5 hour. Yeah. Okay, great. 2.5 hour class. Because guys, generally this is our lab session, but we can't do any labs, so we have to go with theory. And also because of this 1 week break, we are a little bit behind our schedule. So, and after next week, you guys getting a break, your mid-semester break. We are not allowed to teach during that also, because I think we take thinking you guys need a break. But that's okay, guys. So we can easily cover the syllabus. You don't need to worry about that. Okay, so yeah. Guys, tell me whether you all got the answer. So you need any help with this problem? Guys, are you all okay? Okay, great. Okay, guys, I think most of you got the answer. Okay. Okay, now it is a transient behavior of this inductor. Before that, guys, I'll discuss about like okay, now guys, we have inductor. If you watch that video, guys, they are also you know. So how we okay, in a circuit, what are the components that we identified as inductor? They are coil, right? Basically, and also we have ferrite core in the middle of that coil. So now, guys, in a circuit, when we have inductors in series, let's say something like this. So let's say L1 and L2, when they are series, total inductance. So what is the total inductance, guys? It will be L1 plus L2. They are similar to resistors. When they appear series, we just add them, okay? For example, this is 10, let's say 10 millihenry. This is also like 30 millihenry. Now, guys, tell me what will be the L total?
40.
Okay, what is it, guys?
40.
So where it is? Where it's coming from? Okay, one of you have enabled his microphone without knowing, I think. Okay, that's correct. Very good. Yeah. So the total that will be 40 millihenry. Okay, guys. Now that's it. Now, so what will happen when we have okay, now let's say this is L1, this is L2. What will be the total inductance here? I haven't given values, guys. Okay, so yeah, so how we calculate this one, guys? 1 over LT, that is equal 1 over L1 plus 1 over L2. Or maybe if I want to get what is LT, that should be 1 over L1 plus 1 over L2. You guys agree? Guys, you guys agree? Okay, very good. Now I'm going to give some values here. So what will be the total inductance? Now this is 10. So this is, let's say 30. Now what will be the total inductance when they are parallel? Yeah, very good. That's correct. Your answer is correct. Yeah, Jayakumar, that's correct. Guys, what is the total inductance here? So now when they are parallel? Yeah, very good. Guys, yeah. Very good. Yeah, that's correct. Therein. Guys, okay. So tell me your answers, guys. Yeah, very good. Guys, most of you got the correct answer. So how we calculate is, so that is L, sorry, so let's say L total, that is equal 1 over 10 plus 1 over 30. So then you will get 7.5. Okay. So these are millihenry. So because of that, I haven't given it earlier. So answer should be millihenry. Okay. So in that way, you can calculate it. Okay. Guys, you all clear about this series and parallel inductors? So that is how we calculate total inductance. Okay. Okay, guys. We'll go back to our slides. Okay, guys, now think I have a conductor. So let's say, so the inductor, like it is 10 millihenry. And also I have 4, let's say this inductor over here. So I have current flow of 4 ampere. Okay. Now tell me what is the energy stored in this inductor? What is the energy stored in this inductor? Okay. Tushan, that answer is correct. Yeah. Guys, tell me, guys, others. So what is the answer you got? And that's correct, Ahi. Jason, that's correct. Yeah. Other student, guys, you got the answer? Yeah, that's correct. I'll do it, Jayakumar. Okay, so now this is how we will give a little bit of time for others. Then I will solve it. Yeah. So because it is energy, Tushan, energy we calculate with joule, right? So the answer is in joule. Guys, you all got the answer. So now this is how we solve it, right? So the equation, that is E is equal half L I square. Okay. Now here half L 10 to the power -3 multiplied by I mean 4 square. If you solve this one, guys, you will get the answer 0.08 joule. Guys, you all got the answer? Is that clear to you now, guys? Like capacitors, same way. Yeah, so we can solve this for inductors, but now in this situation, we are worrying about current, not the voltage, right? But capacitor, we are worrying about the voltage. Okay. Guys, you all got this answer? Now, guys, if you look at this circuit here, what happened is, so this inductor store energy as magnetic field, okay? Magnetic field. What happened in this resistor? It dissipates power as heat, okay? So if you look at in a circuit, when we have resistor dissipate power, and inductor, it is not all about loss of energy. So it stores this energy in a magnetic field, okay? That is what happened. If you guys are okay with this calculation, so then guys, let's move into this transient behavior of inductor. Now guys, capacitor. So when we study about capacitor, so when we apply some voltage rise like this, okay? In capacitor, it end up with Vs or supply voltage. Now same way, in inductor, current increase like this. Okay, current increase like this, similar to voltage in capacitor. So it take also 5 time constant for this one, but time constant in inductive circuit, this is how we calculate it. So in capacitor circuit, so we calculate the time constant like RC. But inductive circuit, tau is equal L divided by R. So for example, if this is R, if this is L, that means inductance. So the time constant of this circuit, that is L divided by R. So then, so this time interval is actually 5 time constant. But way we calculate the time constant, it is different. It is L divided by R. And also, inductor current change similar to voltage in capacitor. And eventually, guys, it reached the highest possible current of that circuit. What is this highest possible current in circuit? So highest possible current, guys, when we have resistor, when total voltage appear across this resistor, then we can experience highest current. For example, eventually this inductor become a short circuit. When it is saturated, it become a short circuit or just acting like conductor. When this is acting like a conductor, how we calculate the current? So it is simply, if this is Vs, it is Vs divided by R. This is the current through this circuit. Is that clear, guys? Okay, guys, is that clear to all of you? Time constant of inductive circuit and also the total maximum current that we can have in this type of a circuit, and also total time like 5 time constant. Are you guys okay? Okay, guys, let's move to next slide. So here, this is how current grow, guys. So, and also when it is discharging, it has this shape. Okay, and also it takes 5 time constant, same as capacitor, but here we speak about the current. So we will do some examples, guys, then you will understand this. Okay. Okay, now, so these are the universal equation which describe the behavior of this inductor. So now if you look at this, guys, so if you apply this to inductor, so here you can see this one. So this is L divided by R, okay? L divided by R, time constant is L divided by R. Because of that, eventually this become R3 divided by L. So this is how you get it. T divided by L divided by R. When you multiply both denominator and numerator by R, you get RT divided by L. Okay, that is how you get this value. So then we'll derive equation for the inductor charging. Okay. Guys, if you guys feel is it too much today, so I can jump into some questions, okay, without discussing this transient part. So shall we jump into question that we saw in earlier? What you guys think? We can discuss this part, guys, on our Wednesday's class. Okay, I think so we can learn a lot today. So we'll jump into some questions. Okay, then. Okay. Before that, guys, I have put one the video, 5 minutes video. Just watch that video. It is about inductance, mutual inductance, and self-inductance. Can you guys watch that video? So I'll play it here also, okay? go to Moodle. Here, guys, if you go to this electromagnetism, so I'm referring to this third video, guys. No, fourth one. Just watch this video,
Before
guys.
moving on to circuits with inductors, let's have a look at mutual inductance and self-inductance. For mutual inductance, we're going to take two coils, the first with N1 turns, the second with N2 turns. And what we're going to do is ramp up the current I1 in this coil here. Now if we do that, the magnetic field created by the coil is going to increase in magnitude. And what's going to happen is that the magnetic field lines will go through these coils and create an increasing magnetic flux to the right. And so we're going to have a magnetic flux phi b in this direction that will be increasing because we're increasing I1. And what's going to happen is induction. The increase of the magnetic flux in that direction is going to cause the induced current to create a magnetic field going the other way to reduce the increasing magnetic flux. And to do that, it must send a current through this way, in fact. And it can do that because it's going to have an induced EMF, epsilon 2, that appeared because we changed I1, which changed the flux of B through this coil. So basically we increase I1, the magnitude of B goes up, and the flux this way increases, creating an induced EMF across the second coil. So the second coil is made aware of the first by changing the current in it. And in fact, epsilon 2 from Faraday's law, we know is going to be proportional to d phi b over dt, but phi b itself is proportional to I1. And what we're going to write is that it's m21 d I1 over dt. And m21 is a constant coefficient, and it's actually called the mutual inductance. And the mutual inductance has a unit that's called Henry. But we'll get to that in just a second. So this is epsilon 2, and it is generated because of the change in I1. We ramped up I1. Now you could argue, well, wait a minute, could I not do the opposite? Could I not just run I2 through this one, increase it, and then make the first coil aware of the second with the same kind of experiment? And yeah, sure, you could. And you could also write, if you do that, that epsilon 1, the induced EMF you'd get across this coil would be m12 di2 over dt. And that would be a coefficient called the mutual inductance, and the truth is m12 and m21 are equal, so we'll just use m. And the unit is Henry, which is denoted by uppercase H. So this is the mutual inductance coefficient, and we use it when one coil has an effect on another, either this way or that way. Now that's mutual inductance. Let's look at self-inductance, because the truth is, if we just consider one coil, let's say it has N1 turns. Doesn't really matter, but let's just take that coil from over there. And we ramp up the current through it. Well, if we do that, we increase the magnitude of the magnetic field. And really what we're doing is increasing the magnetic flux in this direction through this coil. So if we increase I, the coil is going to be like, wait a minute, we're increasing the magnetic flux this way. I'm going to oppose that, and I'm going to induce an EMF across this coil that will generate a magnetic field that goes this way thanks to an induced current. And this induced EMF, which is going to be called simply epsilon because we don't need to distinguish 1 and 2 here, is going to be related to the derivative of the magnetic flux, to d phi b over dt, but really phi b is proportional to I, so therefore it's going to be minus L di dt. And L is called the inductance, and also measured in Henry. So L is called the inductance of the coil, and it is measured in Henry. So in fact, the coil on its own can react to an increase in current.
Okay, guys, you all watched that video. So that describe inductance and mutual inductance and self-inductance. Okay. Okay. Now, guys, we'll come back to our slides. Guys, now attend these questions. So I told you guys by end of this class, you should be able to answer these questions here. Okay. So I think, guys, your slides not appear like this because I when I open this on my iPad, so it appear like this. Okay. So, okay. Guys, you all watch the video? Okay, great, guys. Now attend this question. Part A, state and explain Faraday's law of electrostatic induction. Okay, guys. Now, so how you answer to that part A? State and explain Faraday's law of electromagnetic induction. So what does it mean, guys? So voltage induced in a coil, guys, that is equal to, it is different version of this, guys, okay? Change in the current multiplied by induction, okay? Voltage induced in a coil is equal to magnetic induction multiplied by change in the current, okay? So then in that way we can get voltage induced, okay? Is that clear, guys? That is how we answer to part A. So in other terms, guys, if you write this direct law, even that is okay. So Faraday's law, according to Faraday's law, we call voltage induced in a coil, that is equal to the number of turns multiplied by change in magnetic field, okay? The relation between current and magnetic field, when we change current in coil, it create magnetic field, change in magnetic field as well, okay? Okay, is that clear, guys? That is the answer to part A, okay? Guys, is that okay? Okay, now so this part B, we have to explain how we get this one, right? V int, that is equal negative n d phi over dt. Here's the thing, guys. This part coming from Faraday's law. According to Faraday's law, voltage induced, that is equal number of turns multiplied by change in the magnetic field. So now this one coming from Faraday's law. This negative sign coming from Lenz's law. According to Lenz, so the voltage induced should be opposing the change in the magnetic field. So that is how you explain this part B. This negative sign coming from Lenz's law, this part coming from Faraday's law. Is that clear, guys? When you are asked to write that Lenz's law and Faraday's law, maybe you can write that sentence that you can find on slides, okay? So, but general idea, voltage induced should be equals number of turns multiplied by change in the magnetic field, okay? I hope that is clear, guys. Guys, are you all okay with part A and B? Guys, are you all okay? Okay, great. Guys, you all okay? Okay, great, guys. Okay, great. Now, guys, okay, now you watch that video also, guys. Explain how mutual inductance applies to working of a double wounded transformer. Now this one, guys, so mutual inductance we speak about when we have two windings. In transformer, what happen is we have two winding like this, okay? Here have magnetic core, okay? Now here what happened? V is equal L di over dt. Now what happened is like when we apply some voltage, so and also when we change this current across this primary winding, it creates some inductance, okay? So inductance. So and also so it induces some magnetic field in this second winding also. So there also we call this inductance, it is shared between these two, mutual inductance, okay? So then V2 is equal L di over dt. So this change in magnetic field create, so here we have some mutual inductance and create some, yes, Derin, is there any question?
Sir, will you be uploading this to the model site?
That's correct. Yeah, I'm going to upload it. It will take a bit of time, guys, to process this video because yeah, it's long class. Okay. Yeah, I'm going to upload. Okay, guys. Now, so there's a mutual inductance between these two. So because of that, it creates current across this also. Okay. So because of that, you can see voltage. Now this is what happened in a transformer. Double wounded transformer mean, guys, we have two windings, primary winding and secondary windings like this. Okay. So this voltage appear across the secondary winding because of this concept, mutual inductance. Mutual inductance is the one responsible for this. Okay. This one, mutual inductance, is shared between primary winding and secondary winding. Is that clear, guys? Is that clear, guys? Okay, guys. Okay, great. Okay, great. Now, guys, self-inductance means, so self-inductance is inductance in one inductor. Okay. So this is what happened. So when we have current through this one, so we can observe this inductance through this coil. So now, guys, so the self-inductance, so we have something that important. When you answer this third part of this one, AC current is something like this. It changed the direction, right? So now it induces also some inductance in this coil, okay, and also magnetic field. So what will happen when we have this type of current through this one? Let's say this time interval is like 0.01 millisecond or second. So what you can think about total inductance here? So the magnetic field of this type of coil due to AC signal, AC current, guys, it is 0. Because here you will, yeah, because we have two opposite direction of the current, right? So then total answer to this one, it should be 0. Because due to change of this current, it is always changing. Then, guys, what you think? So V induced is equal L di over dt, right? Now, to induce a voltage, this current should change. Okay. Now, can we use DC current with transformers?
No.
Yeah, very good. Reason why we can't?
Because transformers are only for AC current.
Yeah, because AC current change this current all throughout the period, right? When we are changing only, we induce voltage. Otherwise, no voltage, right? So DC current means it's flow like this. There's no change in the current. So then DC current can't create any voltage in transformer. If you apply battery, so through transformer, so you can't see any voltage in the secondary winding. Reason? Because of this Faraday's equation, right?
Right.
So then conductor like this, what you have is self-inductance, and you can watch that video again, guys. That is how we explain it, okay? These two occasions. Impact of AC, that is 0. Total, there's no, no magnetic field.
Yeah.
Now, guys, so how you answered this part D? Guys, you all clear about this part C?
Yeah.
Okay. Okay, guys, now tell me how we attend this part D. In the figure below, a conductor is placed as shown between the faces of permanent magnet. Yeah, so then we need to decide the direction of the force. So how we decide? Now, what is the direction of the magnetic field? It is north to south, okay? You guys agree? So like this. What about the magnetic field, guys? So it is, when you apply right hand grip rule, yeah? So it is inside the tab or maybe inside the paper. So that means direction of this magnetic field, it should be like this, right? You guys agree with, like this. So now you guys can see, okay, so this top part, they should repel, okay, this magnetic line, they are same direction. But if you look at this part, so what happened? They are opposite side, they should attract. That means final movement, direction of the force downward. You guys agree?
Yeah.
Guys, you all clear? Guys, I hope it is clear to all of you, right? So
Yeah.
here we are applying right hand grip rule, okay? So yeah, good. So we are applying right hand grip rule. Okay, guys, now, great. Okay, now guys, so the method that we use, guys, it is this right hand grip rule, okay? So now part T, answer to part T, an EMF of 20 volt is induced in a coil of 250 turns when the flux linking with the changes by 10 meters Weber. Okay, 10 milliweber, okay, sorry, 10 milliweber. Find the time in millisecond in which flux makes the turn. What is the equation we apply here, guys? We have number of turns, and also here we are speaking about change in the magnetic field. So because of that, we need to apply this equation here. V induce, that is equal V induce turns d phi over dt. Now guys, what we don't know here is dt. We don't know what is that duration, right? We know what is the change of the time, the magnetic flux. It is given 10 milliweber. So then we can put the values. Voltage induced, that is 20. Number of turn, that is 250, multiplied by change in the magnetic field, that is 10. 10 to the power negative 3 minus 3 Weber, divide by dt, okay, or maybe you can say delta t, that means change. So now dt is equal 250 divided by
10 into 10 raised to minus 3.
Yeah, 10, yeah, that's correct. Divide by 20,
by
right?
20.
Yeah. Now tell me the answer, guys, here.
$0.125.
Yeah, very good. 0.125. So here we need to give it like yeah, in millisecond. So then in millisecond, so this is 0.125 or 125 millisecond, right? You guys agree? Guys, yeah. Guys, you all okay with this answer?
Yeah.
You all okay? Yeah. Okay, very good. Guys, I hope that is clear to all of you. Okay, very good. Yeah. Then guys, okay, calculate the energy stored when current of 15 ampere. Yeah, question is on the slides. Answers are actually, I haven't put answers, guys, okay? One thing we can do, like if somebody take good note, we can share on the Moodle, guys. How about that? So we can ask like one of you to share it. Okay. Okay, guys, part F. Okay, we have 15 ampere current flow through coil. Inductance is 150 millihenry. So now what will be the energy stored there? E is equal half Li square. So now inductance is 0.5 multiplied by L, that is guys 0.150 multiplied by 15.
Square.
Yeah, 15 square, very good. So what will be the answer?
16.875.
Okay. Yeah. 16 point. Very good. Yeah, that's correct. 875 joule. Guys, you all got this answer? Guys, you all got the answer? Okay, great. Yeah. Okay. Now, guys, the part G, inductive circuits. So they are like when we change the current very rapidly. Just think about. Okay, guys. Now look at this one. Okay, part G. Now, if you read this question, the circuit given below need additional protection. Sketch this onto diagram and explain why it is required. Okay. Okay. Now, no, that's okay, Jayakumar. That's okay. Okay. Now, guys. Now, if you look at this equation, V induce is equal L di over dt. Now, guys, when we quickly turn on and off switch, we change current very rapidly within maybe few milliseconds or maybe few microseconds. That means T go very small number. That means this term go very high number. Then what happen is V induce become very big voltage. Maybe it can be like 200,000 voltage. So this effect is not good to circuits or maybe transistor like component. So because of that, occasion like this, we need to put protections. Okay, that is why we need to put protection across this circuit. The protection that we put, guys, we should put diode like this. Orientation is also important, guys. Okay, so diode current flow happen from positive end to negative end. Okay, so this is the symbol of diode. Current flow from this direction to this direction, right? If you put it opposite direction, it short circuit this. It creates some current flow through this one. Okay, and it will definitely burn the transistor. Here, what happened is when we turn on and off this switch, it creates back EMF, right? Reverse side voltage. Because of that, when you put diode like this, it circulates that current only through this inductor, not through the transistor. It bypasses that current. For that purpose, we are introducing diode like this as a protection. That is important, guys. I have seen this question in many papers. Okay. Is that clear, guys? You all got it? We can put diode like this to protect this transistor, not the inductor. Inductor can handle high current, okay? But this transistor can't. So because of that, we put this current, the diode, so it bypasses that reverse voltage we create. Here, guys, by using this equation, I show you how we induce very big voltage, because within very small time duration, we change the current in the circuit, okay? So then it creates very high voltage. Maybe it can be like 200,000 volt. So that is harmful to your transistor like component in the circuit. Because of that, to bypass that sort of current, we put diode like this. Is that clear to you guys? Only thing you need to memorize, guys, you need to memorize this, understand this orientation. You should not put in this direction. So then it definitely short circuited, okay? We should not put it like this. This is the direction. When this is a plus, so cathode of the diode should connect with this positive terminal like this. Guys, is that clear? Clear to all of you? Guys, is that clear?
Yeah.
Guys, you all okay, guys? Okay, Darren. Okay, guys, is it all clear to all of you? Yeah, Ahi, okay. Guys, all of you, is it clear? Yeah, great. Guys, okay. I hope you guys enjoyed the class, but you need to spend 5 minutes, guys. One thing till I take attendance, you have small activity, guys. If you, okay, I'm going to share the screen again.
Could I just ask one question?
Yeah, that's correct. Yeah.
Our results from our electrical PowerPoint, have you marked them yet?
You mean the lab?
Yeah.
No, I haven't marked them yet. I will
Okay.
soon upload it, guys. Okay.
Okay, that's all good.
Okay. Okay. So now you can see my screen. Guys, okay. So if you go to this magnetic section, guys, so at the bottom, I have created a small forum, guys. Okay. Now, please share your opinion, guys, like what went well in the class, whether you enjoyed the class, and also yeah. So guys, I think you all can put create a topic and put some feedback over here, right? Guys,
Okay.
please share your opinion, what went well, and also what need to be improved. Likewise, please put a feedback, all of you guys. Okay. I'll take your attendance, guys. Till then, please go to this place. So you can find it here. If you go to your course, electrical principles, under this electromagnetism, okay, under this one, guys, at the bottom, you can find this share your opinion here forum. So create a post there. So please share your feedback. Okay, I'll take your attendance. I hope you all okay with the location.
Shall I go?
Yeah, that's okay.
Shall I left?
Yeah, that's okay. Jason, Carlos, you guys have class tomorrow, okay? Guys, can I have that class about 9 o'clock? Or morning also? Okay, Carlos, are you online?
Carlos, hello.
Carlos, yeah, yeah. So you're online, right?
No, Carlos.
No, Carlos. Yeah. Yeah. So then, Carlos, can you join with the class tomorrow 9 o'clock? Okay, that's great. Jason, you have contact with who? This Chen? Jason?
No, Jason either.
Yeah, Jason is here. Please give some message to him, okay? Join with the class tomorrow morning. Like this, I will create a link, so then you guys can join there, okay?
When is our next class?
Wednesday morning. For all of you guys, so next class is as usual, Wednesday
Okay.
morning.
8 a.m.
8 a.m. Yeah.
Okay.
Okay, guys, I hope you guys enjoyed. Some of you attracting well, like very interactive than even the usual class. That is really good, guys. But anyway, so we have to manage with available resource, guys, okay? So be patient. So we'll do it in this way. And also I will consider your feedback, guys. If you have something, guys, please let me know, like so I'm happy to change the mode and anything.
Mocha.
Can I ask you about that assignment question?
Yeah, that's okay.
Yeah. So for question 1, the circuit, the 12 volts, 20 amps, is it a series circuit? So the current 400 milliamps at
That's
so
correct.
I2 is equal to I1?
Yeah, that's correct. It is series circuit, current is same. Yeah.
Oh, so it's the same. Okay, cool.
Yeah.
That's all I was trying to figure out how to start it.
Okay.
Okay, now thank you.
Okay.
Cool.
Okay, guys.
So you know the test we were meant to do last week?
Sorry?
You know the test we were meant to do last week?
That's correct. Yeah. So I send you guys message like so because we didn't have any classes last week, we canceled all of them. So I created the assignment. Okay. So now assignment is equal to that test.
How do we access the assignment?
Yeah. So shall I show you?
Yes, please.
Yeah. So just I'm going to share the screen. Okay. Screen. So if you go to Moodle site, okay, now under this assessment and resources, go to this assignment 1 link, okay.
And how long do we have to complete it?
So the due date I put, so let's see, guys. So it is 6th of April.
Okay.
Should be all right, right? Because I'm planning to discuss some questions during
on Wednesday.
Yeah, Wednesday as well. Yeah.
Oh, yeah.
I think it is feasible. Like you guys can easily do it.
Yeah.
Okay.
Okay.
Okay. Guys, any other question?
No, thank you.
Okay. Are you all okay, guys? You guys enjoyed the class? All of you?
Yeah. Do you have any update for us about what's going to happen within the next, 2 or 3 months regarding WinTech or no?
Actually, I don't have that information, but guys, as long as possible, like we will run online. I think it will go beyond 1 month. That is what I feel. So
yeah,
that 1 month thing is not very certain. So till they control the this virus issue, so they will we have to meet online. But we'll see, guys. At least by the time of your exam. So if it is finished, that's good. So such that we can have your exam. So then WinTech will decide, guys, what to do next. Like sometime, not sure whether they will ask you to come for only for the exam and sit and likewise.
So
no
at
idea.
this stage, exams are still running in the same time
That's
frame.
correct, yeah. At this stage, so we think we will have exam during that time slot.
Oh, wow, that'll be hard.
But I will update you guys once I get the information. Even you will get emails from the administration.
Yeah.
Any other question, guys? All good?
All good.
Okay. I hope you guys enjoyed the class. Okay. Okay, shall we finish it then, guys? See you all on Wednesday. Guys, see you all on Wednesday.
See you.
Yeah. See you
Have
guys.
a good day. Stay safe.
Yeah, you guys. Okay, enjoy the rest of the day, guys. Okay, see you guys. So enjoy the rest of the day. So we'll see you again on Wednesday.
Yeah.
Thank you guys. Okay. Thank you for tolerating me for last 3 hours. See you all. Guys, do you want me to leave this open, the meeting, or shall I close it? I think I don't have option to leave. Okay, I'm going to close it, guys. Okay.
Okay.
See you guys.